Hello everyone, I'm Xinben, a student from University of Science and Technology of China. I'm under the guidance of Zhang, who is the corresponding author of our research. Today, I'm excited to present our work, PCAT, Functionality and Data Stealing from Speed Learning by Pseudo-Client ATtack. I will introduce our work from 5 sections, and let's start with background. Speed learning is a promising approach in distributed machine learning, specifically designed for data owners with limited resources. It allows a powerful server to handle the majority of computation by splitting a neural network into multiple parts, which generates different typical settings. In a single client setting, the main difference from centralized learning is that the client sends smash data to the server during forward propagation, while the server sends gradients during backward propagation. This seemingly provides privacy protection for the client's data. But is that true? Is there any risk of leaking private information? Previous studies have demonstrated potential privacy leakage in speed learning. For example, FSHA proposed a malicious server that could hijack clients and extract essential features from their raw data. However, this approach changed the learning task and disrupted the learning process, preventing the attacker from stealing the client's functionality and labels. Another attack called unsplit shares similar settings and goals with our research. However, in practice scenarios, this attack often fails to achieve its objectives. Thus, in this work, we consider a more general and challenging problem: how to steal the functionality and data of the client model in an oblivious way when the structure of the client model is unknown and when tasks and client models are more complex. Also, our attack should be suitable to all 3 variants of speed learning and remain resilient against some defense methods which the client may employ. The only assumption is that the server has a tiny dataset for the same learning task. Now we introduce some interesting observations. We set functionality stealing as our major attack because once we have stolen the client's functionality, data reconstruction becomes attainable. Consequently, we explore how a small dataset can be utilized to steal the functionality of a model trained on a large dataset. We examine 2 scenarios: stealing a complete model and stealing a client model. Furthermore, we explore 2 attack strategies: stealing after training and stealing while training. We first investigate stealing a complete model. We adopt the main idea of knowledge distillation, where the victim model teaches the attack model, enabling the attack model to steal the functionality of the victim model. Stealing after training involves the victim model use its well-trained model to teach the attack model. A more advanced approach is stealing while training, where the attack and victim models are trained synchronously, and in every iteration, the victim model teaches the attack model. Our experiment result shows that although the initial learning targets are not as accurate as the final target, actually the evolving learning targets can guide the attack model to converge more precisely to ultimate targets. Then we focus on stealing a client model. We need to address 2 challenges. First, the attack client can't directly access the victim client, but only obtain the server model. Second, the attack client can't feed data to the victim client and get soft labels generated by the victim client. Thus, we provide a solution. As for stealing after training, we fix the server's parameter after its training and only train the attack client based on the small dataset. According to the experiment result, with the constraint of the server, the attack client optimized the feature space of its output to closely align with the feature space of the victim client's output. In this scenario, the learning target becomes the feature space rather than the soft labels. For stealing while training, the attack and the victim clients are trained in parallel. In every iteration, the server and the victim clients are trained on the large dataset, updating their weights. The attack client is trained with the server on a small dataset, but only updates its own parameter. Similar to stealing a complete model, a series of intermediate server models during split learning can significantly improve the attack client's accuracy. Based on these valuable insights, we introduce our proposed attack, Pseudo-Client ATtack. In this attack, the server initializes a pseudo-client model with any structure before split learning begins. Similar to stealing a client model while training, the server trains the pseudo-client to map inputs to the feature space of the victim client's output. Once the pseudo-client achieves similar functionality to the victim client, it can replace the victim client and perform inference without the victim client's cooperation. Then, using the pseudo-client model and the smash data of the client model, the server can reconstruct the private inputs of the client by learning a reverse mapping, as well as their corresponding labels. To demonstrate the effectiveness, we use vanilla PCAT to represent stealing after training strategy. It is worth noting that our attack can be easily extended to multi-party and U-shaped split learning. To enhance the effectiveness of PCAT, we need to pay attention to certain implementation details. First, aligning label is crucial. In each iteration, the server aligns the labels of the training samples for both the pseudo-client and the victim client. This process helps reduce the gap between pseudo-client and the victim client. Secondly, we employ a late start strategy, which involves skipping some initial iterations before the victim client starts to converge. This approach helps avoid misleading the pseudo-client. We have observed that selecting a more appropriate start point leads to better performance of the pseudo-client. Now let me show some attack results. We implement PCAT on 3 datasets, MNIST, CIFAR10, and Tiny ImageNet. Their corresponding authors are LearnNet 5, VGG16, and MobileNet. We first launch our pseudo-client attack in the case that the data in the pseudo and victim clients are i.i.d. Through the result, both vanilla PCAT and PCAT outperform independent training, which only relies on the attack dataset. Also, through converging slower, PCAT achieves much better accuracy because of the guidance of evolving server models, which drives the output feature space of the pseudo-client model closer to that of the victim client model. Then we consider the cases that the pseudo-client dataset lacks one or more classes of training samples. If we use independent training, the pseudo-client can't recognize the missing class at all. However, PCAT significantly mitigates the effect of the missing class. Therefore, we conclude that PCAT is robust to non-i.i.d cases. We evaluate PCAT in cases that the structure of pseudo-client model is simpler or more complex than the victim client model. Both tables show that a more complex pseudo-client model can achieve almost the same performance as the same structure does. Thus, the knowledge of the victim client model structure is not necessary. If the victim client adopts some privacy defenses, such as adding DP noise and no-peek defense, PCAT can still work well, since the accuracy gap between the pseudo and the victim clients is steady regardless of the type and the strength of the defense. We are also surprised to find that adding appropriate Gaussian noise to the smash data can improve attack performance. Compared with the state-of-the-art methods, PCAT performs better to a great extent in every attack goes. Here, we summarize our work. In this study, we propose a novel attack called Pseudo-Client ATtack in various speed learning settings. PCAT enables a semi-only server to conduct functionality stealing, input data reconstruction, and label inference without knowing the structure of the victim client model. Comprehensive experiments demonstrate that PCAT works effectively for rich models, tasks, and settings. The whole attack process is transparent to the client, which thus reveals a serious privacy risk of speed learning. That's all my talk. Please feel free to ask questions or reach out to us for further discussions. Here is our information.